if I were a better person, I would have added this at the beginning of the end of the last video. But the point of this example was to bring up that integration gives us, let's give ourselves just a hair of room here, signed area. Right? I've mentioned this before, where area above the x-axis is counted as positive area, and area below the x-axis is counted as negative area. So let's continue this idea with another example, and we're going to take a look at this example, we're going to integrate it, and then we're going to take a look at the actual geometric meaning of this. So first and foremost, let's just plow forward and integrate this thing. So the integral from -2 to 2 of the function t squared minus 4 dt. Well, we know how to integrate this. Again, just ignoring the bounds of integration for now, we're just going to find the antiderivative of t squared minus 4, or integrate t squared minus 4. So using the power rule, we see that 1 over 3 times t to the third power has derivative t squared minus 4. What has derivative of 4? Well, 4 times t has derivative of 4. Now we take into account the fact that we're doing a definite integral, and so we're going to evaluate this from 2 to -2. And that means take the expression and evaluate it at t equals 2. So 1/3 times 2 to the third power minus 4 times 2, and subtract it by evaluating the same expression at t equals -2. So 1/3 times -2 to the third power minus 4 times -2. A little bit of algebra flying around in here. What are we going to end up with? Well, 1/3 times 8 is going to give us 8/3 minus 8 minus parentheses. We'll worry about sorting that out later. -2 to the third is -8 times 1/3 is -8/3, and plus 8. -4 times -2 is positive 8. So now let's tidy that up and get rid of our parentheses. 8/3 minus 8 plus negative times negative is positive 8/3, and negative times positive gives us -8. So we end up with 16/3 minus 16. Well, that's 16/3 minus 48/3 when you get common denominators and you do the subtraction, and we come up with a final answer that this integral is equal to -32/3. And it might be helpful to approximate that as -10.7, just to get a loose idea of what it is. So what is the geometric interpretation of this? Now we're talking about the geometric interpretation of this. So geometrically, we have that t squared minus 4 is our standard parabola shifted down by 4. So 1, 2, 3, 4. This is your t-axis, and this is your f of t-axis. And then, so it's going to cross the axes at +2 and -2 respectively. And so t equals -2 there. Sorry, I forgot my negative. -2, and then t equals 2. That means that this integral calculated the signed area trapped by this curve between the x-axis. And so what this tells us is that the signed area, and so I put it as quotes, is equal to or -32/3, which is about -10.7. And if we did this on a grid, you could probably count out that there were about 10.7 squares in there, square units. So yeah, let's plow forward and do lots more examples of these. Okay, so we're not going to take a look at the geometric interpretation. This is just time to practice definite integrals using the fundamental theorem of calculus. So what has derivative 4x? 4 times e raised to the x. Well, you could pull the 4 through that integral, and then left with e to the x dx. And what has derivative e to the x? Well, just e to the x. So this is 4 times e to the x, and then we're going to evaluate that from 2 to -2. And so top minus bottom, we're going to take 4 times e raised to the second power and subtract 4 times e raised to the negative 2 power, which is a fine answer here. I would actually go ahead and tidy it up as 4 times e to the second power minus 4 over e to the second, because I kind of like it that way a little bit better. But either one is a fine answer, a nice exact answer. And a calculator could give us a decimal approximation if we're actually interested in the actual a number that meant something more to us. Okay, so let's do an exponential one. What has derivative 4 to the x power? Well, 4 to the x power would have derivative ln of 4 times 4 to the x, so we have to kind of counteract that ln of 4, so we'll take it 1 over ln of 4. That'll deal with that part. There's our antiderivative, and we're going to evaluate that from x equals to 4 to x equals to negative 3. I'm just kind of, you don't have to use the x notation. If you like it, great. Like I didn't do it here, but I did do it there. Either way. So top minus bottom, we're going to evaluate 1 over ln of 4 times 4 raised to the 4th power minus 1 over ln of 4 times 4 raised to the negative 3rd power. And again, you could leave it like that, or you could rewrite your second guy with a positive exponent as 1 over ln of 4 times 4 to the 4th power minus 1 over 4 to the 3rd power times ln of 4. Okay. So once again, let's just plowing recklessly forward here. How do we integrate the square root of x? Well, we take it and we first rewrite it as a power so we can apply our power rule. And we've done this before, so I'm going to go fairly quickly here, but x to the 1/2 plus 1 gives me 3/2, and you're going to multiply by 1 over that, so multiply by the reciprocal of that, 2/3, and then evaluate this from x equals 16 to x equals 0. What do we end up with? Here I'm going to, we'll start right here. Okay, so we have top minus bottom. 2/3 times 16 raised to the 3/2 power minus 2/3 times 0 raised to the 3/2 power. Well, 0 raised to the 3/2 power is pretty nice. 0 to any power is just 0. Anything times 0 is that. So what is this 2/3 times 16 to the 3/2 power? Well, so that is 16 to the 1/2 power raised to the 3rd power. Or you can do this with roots if you like. In fact, that's what I'm about to do now, is convert that 1/2 into a square root. And so that's going to be 2/3 times 4 raised to the 3rd power, which is a relatively big number, but it ends up being, once you multiply it by 2 on top of the fraction, 128 over 3. Last but not least, we've got 1 over the square root of x. Well, similarly, we're going to rewrite this as a power, and that's going to be x to the negative 1/2 power dx. Apply our power rule to get x to the negative 1/2 plus 1 gives me 1/2 multiplied by 1 over 1/2, so multiplied by 2 over 1. And evaluate this from x equals 1 to x equals 9. I said that in the wrong order. Apologies. So sometimes when I see it's a square root, I like to just rewrite it before I evaluate it. 2 times the square root of x evaluated from 9 to 1 gives us 2 square root of 9 minus 2 square root of 1 gives us 2 times 3 minus 2 gives us 6 minus 2, which is 4, a nice concrete answer. One more example and we'll call this video good. So let's do a slightly more complicated one. At first looks, we may look at this and say, oh, heck, I can't do this. But we've already done examples of this. The last 2 examples have been pertinent to this. What we want to do is always, if you see something complicated, you always want to try and do some algebra to tidy. Can I do some algebra to tidy that integrand up into something that I can do? Well, here the idea is saying, hey, this is a root x is a common denominator of 2 fractions that have been added together. I'm breaking the expression up into 2 fractions, which can be a very handy trick in calculus. So the first one would be x over the square root of x minus 1 over the square root of x dx. And individually, we can rewrite that as integral x over the square root of x. Well, that's x over x to the 1/2 power, that's x to the 1/2 power. To see that, what I just did was x over square root of x equals x over x to the 1/2, and you can use the quotient rule or move it upstairs with a negative exponent. Any way you slice it, you're going to end up with 1/2 x to the 1/2 power remaining on top. And then the other one, directly similar to the last problem we did, 1 over root x gives us x to the negative 1/2 power dx. Don't forget your limits of integration, so we'll add those in there now. And now we're ready to integrate. This is something we can absolutely do. So for the first one, we've got x to the 1/2 plus 1 gives me 3/2 power. 1 over 3/2 is multiplied by the reciprocal. Minus, x to the negative 1/2 plus 1 gives me positive 1/2 multiplied by the reciprocal. 1 over 1/2 gives me 2 over 1. And we're going to evaluate this from x equals 9 to x equals 1. Okay, so whoops, sorry about that. Before we do this, I want to just kind of rewrite this thing into a format that might help me evaluate it a little bit easier. As we saw in 2 examples prior, x to the 3/2 can be rewritten as the square root of x to the 3rd power minus 2 to the square times the square root of x from 9 to 1. And now we're ready to do it. Okay, so top minus bottom. So here, whenever I have lots of things that I'm going to evaluate, so for x equals 9 here, I like to put them all in a big parenthesis, and then I'll have another parenthesis for the bottom one, x equals 1. So 2/3 times the square root of 9 to the 3rd power minus 2 times the square root of 9. Now for 1, 2/3 times the square root of 1 to the 3rd power minus 2 times the square root of 1. All right, so in here, before I rewrite this, I'm going to say, hey, that's just 3. And that's just 3 as well. I'm not canceling anything out. I'm rewriting it just to save a little bit of writing. So now we have 2/3 times 3 to the 3rd power minus 6. And I can drop that first set of parentheses, but we'll keep the second one. We'll deal with the distribution once we tidy up the expression inside. 1 to the, well, that's just 1. And 1 to any, root 1 is always 1, and 1 to any power is just 1, and that's just 1. So this is really just 2/3 minus 2. And you could do that in the parenthesis first, but I typically like to distribute the negative sign. Before we do that, we're not going to get sneaky. Okay, so 2/3 times 3 to the 3rd power minus 6 minus 2/3 plus 2 when you distribute that negative sign out. And when you add all this stuff together, this becomes an exercise in algebra, which I'm going to leave to you to verify, but it will give you an answer of 40 over 3. All right, we're going to end this one here.